Hey everyone, I wanted to go over this question from the skill check because a lot of people had trouble with it, and I want to make sure we're all prepared for the next skill check. Now, there were several parts of this question. You could have certified um, verifying that a mapping is a linear transformation. You could certify the subspace proof, or you might be able to certify the subspace counterexample. And I'm going to go over all of these today. We are given this mapping that takes in elements from P2 of R. Remember that these are polynomials of degree at most 2, and their coefficients are real numbers. That's where the R comes from. And it gives back, or it outputs, vectors in R2. In R2. So a vector with 2 elements. And the way that it does that is it takes the polynomial that you give it, and it adds the first 2 coefficients, puts that in the first vector spot element, and then it takes 2 times the third coefficient and puts that in the second element of your vector. So for just some examples to help you like wrap your head around what this does. So let's say if I gave this mapping the polynomial 3x squared plus 2x minus 5, no, let's do minus 10, I don't know. Then the mapping would take 3 plus 2, so do 3 plus 2 here. So that's this first element. And then it would take, use a different color, it would take 2 times this third element. So I'd have 2 times negative 10 here. And so this mapping would produce the vector 5, negative 20. That's like the idea. It just adds up the first 2 coefficients and then takes 2 times the third coefficient. Now the question is to verify that this is a linear transformation. The word verify means that it is going to work. And if you read the explanation of the standard, it just says, I can prove that a given mapping is a linear transformation. So that's what we're trying to show. Let me get rid of this example because an example is not a proof. Let me write that down. An example is not a proof. You can use examples to help you get a handle on what's going on or get a sense of how something is working, but it is not a proof. Okay, so I'm gonna keep that on here because I think some people are still getting confused by that. So let's verify that this is a linear transformation. Our plan for doing that is to show that if I take the transformation of 2 vectors in P2R, then I will get the sum of the transformations. And I also want to show that if I transform a scalar times a vector, I'll get the scalar times the transformation. So we need to sort of identify what these objects are, first of all. So for part A, we need to start with 2 elements in the domain of the transformation. So let's let, hold on, my pen's not working for a second. Let's let y1 and y2 be elements of the domain, and that's P2 of R. Okay, well, let's give these like a little bit more of a structure here. Elements of P2R kind of have this form. So let's say y1 looks like a1x squared plus b1x plus c1, and y2 looks like, we'll say a2x squared plus b2x plus c2, where these coefficients, a1, b1, c1, a2, b2, c2, those are all in R. Those are all real numbers. So a1, b1, c1, a2, b2, c2 are real numbers. Okay. Now I want to show that if I transform the sum of these 2 polynomials, that I get the same thing I would get if I had just transformed each one individually and added them together. So let's look at what t of y1 plus y2 looks like. Okay, we do what's in the parentheses first. So this is t of, I want to add a1x squared plus b1x plus c1. This whole thing is what I'm calling y1. I want to add that to a2x squared plus b2x plus c2. This whole thing is y2. So I'm adding those together inside the transformation. Now let me rewrite this a little bit so that it looks more like, oops, sorry, like this format. So something times x squared plus something times x plus a constant. So let's write it that way. That just means I'm going to group. So I still have t hanging out here. I haven't applied the transformation yet, so I can't get rid of the t. But I just want to rewrite what's in here in a way that groups the powers of x. So I'm going to group everything that has an x squared next to it. Okay. I'll group everything that has, oh, sorry, should be a b here. I'll group everything that has an x next to it. And then I'll group my constants. Now that I have this in this form, I can apply the transformation pretty easily. The transformation said t of ax squared plus bx plus c equals a plus b comma 2c. This says that whatever is on these coefficients on x squared and x, add those together. All right, so here I want to add whatever's here and whatever's here. I'm going to add them up. Let's look at our transformation, or our situation here. This a1 plus a2 is the coefficient on x squared. b1 plus b2 is the coefficient on x. So I'm just supposed to add whatever those objects are. And that goes in the first element of my vector. Now I am applying the transformation, so I don't write t because I'm actually using t. So here I have a1 plus a2, that's what was multiplying x squared, plus b1 plus b2, that's what was multiplying x. That's the first component of my vector. The second component is here, says take 2 times whatever the constant is in this polynomial. All right, if I look back down here, the constant just looks like c1 plus c2. So I'm going to take 2 times whatever that constant is, c1 plus c2. Okay, let's pause this for a second. We just applied the transformation to the sum, and I want to show that this is equal to what I would get if I had done t of y1, like on its own, plus t of y2. So let me pause that and let's compute this. So we have this, and I'll say also, so up here we say like, so we let y1 and y2 be elements of the domain. We showed, like, we just gave them a form, like what do those elements look like? And notice that they are different, okay? I can't say that I'm picking the same 2 elements. That doesn't really tell me anything. I need to pick 2 different general elements. So A1 is here, and I'm using A2 here because I'm specifying they're different. Same with B1, B2, C1, C2. So now we've computed the transformation of the sum. Let's also compute this object, and we hope that these two things are equal. That's what we're trying to show. So let's compute this. Okay. T of y1, that means we're going to apply the transformation to a1 x squared plus b1x plus c1. And then I'm also going to apply the transformation to y2. So I'm going to apply this to a2x squared plus b2x plus c2. So you can see here I'm doing t of y1 and I'm doing t of y2 separately, and I want to see what I get. When I apply the transformation, maybe I'll do this in a different color, to this piece, okay, I'm going to get a vector. And that vector is what has a first element that is the sum of the coefficients on x squared and x. So in this case, that's a1 plus b1. Okay. The second coefficient, this transformation says to multiply the constant in your polynomial by 2. So I have 2c1. Okay. Let's look at this second part. So I'm going to add. When I apply the transformation to y2, the first component of my vector is I'm going to add a2 and b2. And I'm going to take 2 times that third component. And now I'm going to combine these 2 vectors. So a1 plus b1, and I'm adding a2 plus b2. In the second component, I have 2c1 plus 2c2. And here, like if I look back up to this part, when we applied the transformation to the sum, I sort of have this structure. Like I have these two things are equal. I just need to sort of convince whoever is reading this that they are equal. So maybe I could factor out the 2 here and rearrange things. So I could write this as A1 plus A2 plus B1 plus B2. So I'm sort of grouping things together in the same way that they're grouped up here. And then here I could factor out the 2 from the C's. So 2 times C1 plus C2. Okay, so let me like make this a bit smaller. We're not done yet. I just want to get everything on the same screen. So what we just showed, so therefore, t of y1 plus y2 equals t of y1, and then plus separately t of y2. That's one part of being a linear transformation. So if I go back up here, we just showed this first piece. Okay. Now we need to show the second part, that if I take the transformation of a scalar times a second degree polynomial, I get the scalar times the transformation. Okay, I'm going to give myself a new page here, but I'll keep the questions on here. So let me just pull this back up here so you can pause and kind of look at this. And I'm going to assume that I'm just continuing this proof. So I'm going to use y1 from earlier. And what I need now is a scalar. Actually, I'll just give myself a new blank page because the questions are kind of in the way right now. Okay, so we're just continuing our proof. So let's let k be some real number and let y1 be defined as above, just because I don't want to redefine another. I mean, you could redefine another element, but I don't feel like doing it. Okay, then we want to show that if I take the transformation of a scalar times y1, that I'll do some work and I'll get k times t of y1. But you have to show this work. I can't just state that this is equal. Like then I haven't proven anything. I've just sort of stated something. I need to show this is like the bulk of the work. So let's do that. Let's take the transformation of k times, and y1 was defined in this way. A1x squared plus b1x plus c1. Okay, and get rid of this for a second. All right, so this looks like t of ka1x squared plus kb1x plus kc1. And now we're going to apply the transformation. The transformation says that I will end up with a vector. And what goes in the first component is I take the sum of whatever is multiplying x squared and x. So I get ka1 plus kb1. And then the second component is 2 times whatever is sitting over here. I was highlighting that with orange earlier. So this is 2kc1. Now I want to show that this is equal to this is equal to k times t of y1. So let's figure out what this looks like and show that they're equal. So, oops, sorry about that. Okay, also k times t of y1, that's k times t of a1x squared plus b1x plus c1. Now I'm going to apply the transformation, and the k is still sort of like hanging out here. So k is out here, and now I'm applying the transformation. I'm going to get a vector. I'm going to add the two coefficients, and then I'm going to take 2 times the last coefficient, because that's just the rule that I was given for this particular transformation. Now, I want to make this look like this. And the way I can do that is I can distribute the k. So I get, oops, ka1 plus kb1, comma, 2kc1. And now these look equal, okay? These are equal now. So I can say, therefore, t of ky1 equals kt of y1. And since we've showed both of the things we wanted to show, let me go back up here. Hopefully I can maybe zoom out all the way here. Not quite, but so up here we showed that if I take the transformation of the sum, that's like if I had taken the transformation individually and then added them together. And here we showed that if I take the transformation of a scalar times y1, then I get a scalar times the transformation. So because we showed those two things, now we can say, hence T is a linear transformation. And we're done. That's the first part of this problem. Okay, let me add, let me go down to this page now where I've got the question again, because I want to go over parts B and C as well. So if you just wanted to look at part A, you can, turn the video off. But that's how you verify that something's a linear transformation. And I'm going to give you different transformations on different skill checks because you can have a transformation from any vector space to any other vector space. It just depends on how you define it. So you have to understand how it's defined and then show that T of the sum of two vectors is the sum of the transformations and show that T of a scalar times a vector is the scalar times the transformation. So you have to do that procedure, but the transformation may look different every time. Okay. All right. Now, in part B, I used this transformation to define a set. Okay. And the set that I defined is that it takes in, I have, vectors in P2. And then what's special about them is that when I apply the transformation I defined up here, I get 0, 0. So let me show you an example of an element of the set S. And again, this is just an example to give you a sense of what this set is doing. So let's look at x squared minus x plus 2. I'm going to argue, oh, sorry, not plus 2, x squared minus x. Yeah, this is an element of S. The one I just wrote down is actually an element of this set. So let's look at x squared minus x. How do I know that this is in the set S? Well, it's first of all, I know that it's a polynomial. It's a second degree polynomial, or a degree at most 2. But that's not enough to be an S. I need to know that if I apply the transformation that's defined up here, I get 0, 0. Well, let's apply the transformation. T applied to x squared minus x. The transformation says, I want to add up the coefficients on x squared and x. Well, the coefficient on x squared is 1, and the coefficient on x is negative 1. Okay. And then in the second element, I want to have 2 times the constant term. Well, the constant term in this polynomial is 0, so this is 2 times 0. So I do get 0, 0. So this polynomial is in my set S. That is just an example. And remember, that's just to kind of give you a sense of what this set looks like, what types of elements might be in there. But an example is what? Not a proof. Okay. You can give a counterexample to disprove something, which is what we'll do in part C, but it's not a proof that everything is going to work. If you wanted to do that, you'd have to give me an example you'd have to go through every single element in that set, which would again take you your entire lifetime and then some, because there are infinitely many elements in this set. So say it out loud to yourself while you're watching this video. An example is not a proof. Okay, we're all on board. Great. So let's prove this. This is actually going to be a subspace. We can show that, part B. Let's check that the 0 vector is in here. Now, the 0 vector is going to be the 0 vector from this set. So the question is the 0 vector from the second degree polynomials in this set? Well, the 0 vector in that set is the one where it's a function that's all zeros for all values of x. So we have that z of x equals 0. 0 of x equals 0 is the 0 vector in P2 of R. And If we take the transformation and we get 0, 0, then this is also in S. So let's take the transformation of 0. You could think of this as 0 times x squared plus 0 times x plus 0. That's the same as the 0 function. Now let's apply the transformation. The transformation says add up the coefficients on x squared and x and multiply 2 times whatever the constant is. And I do indeed get 0, 0. So z of x equals 0 is an element of S. We need to check that, but this alone is not enough to be a subspace. We have to also show closure under addition. So we need, let me let that go away. We need closure under addition and scalar multiplication. Okay, so you can't stop here, you have to keep going. Okay, how do we show closure under addition and scalar multiplication? We need general elements of our set to prove this. Again, you cannot use an example. Okay, you can't just pick an element and then say that it works or doesn't, that it works. That's not a proof. So we need to let y1 and y2 be general elements of our set. So then we can say y1 is a1x squared plus b1x plus c1, and y2 equals a2x squared plus b2 plus, b2x plus c2. Okay, those are two polynomials. But what I also need to know is that if I apply the transformation, I get 0, 0. So I also need to know and t of y1 equals 0, 0, and t of y2 equals 0, 0. Okay. So I've got two general elements of S. Now I need to show that if I apply the transformation, now I need to show, okay, maybe I'll do this on the side. I need to show that y1 plus y2 is also in S. Well, what does it mean to be in the set S? It means that if I apply the transformation, the one that was defined earlier in the problem, then I get the 0 vector. So let's see if that's true for the sum. So let's apply the transformation. So we have, I apply the transformation to y1 plus y2. I am then applying the transformation to let's see, the sum of y1 and y2 is going to look like this. I'm just grouping them already because I did that argument earlier. So we sort of already know that this is what the sum of y1 and y2 looks like. And if I apply the transformation, I'm going to get a1 plus a2 plus b1 plus b2. And then I'm going to get 2 times c1 plus c2. Now I want to use the fact that y1 and y2 are already in S. That's already something I know. So I know this is equal to a1 plus b1, 2c1 plus a2 plus b2, comma 2c2. And I actually know already that these two elements, or these two terms are 0, 0 and 0, 0. The reason I know that is because this, so maybe I should write this first. This first part here is actually t of y1. So this is t of y1. And this second term is t of y2. And I already know that these are equal to 0, 0 and plus 0, 0. So I do get 0, 0. So when I apply the transformation to y1 plus y2, I get the 0 vector. Okay, so here I would say, therefore, y1 plus y2 is in S, and S is closed under addition. So that's one part of the subspace proof. Let me get some more paper here. Now I need to show that the set is closed under scalar multiplication. So let's let k be a real number. Okay. Then I want to consider t of k y1, and I want to show that I get 0, 0, because that is what it takes for k times y1 to be in the set S. So this looks like t of ka1x squared plus kb1x plus kc1, which is equal to, I'm going to apply the transformation now, ka1 plus kb1, comma, 2kc1. But if I factor this out, the k, I've got a1 plus b1, comma, 2c1. This is t of y1, which I know is 0, 0. So k t of y1, and I know that's k times 0, 0, which is 0, 0. Okay. Therefore, ky1 is in S, and S is closed under scalar multiplication. Okay, now since we've got the 0 vector, we've got closure under addition, closure under scalar multiplication, then we can say hence S is a subspace of P2 of R. Okay. So that was part B, showing that we've got a subspace. And then part C asked you to figure out whether a similar set is a subspace. And in this case, T of our polynomials gives you 0, 4. This is not going to be a subspace. So you could try to prove that it is, and you'll run into some problems. You could also notice that the 0 vector is not in this set. So let's like look at a few different ways we could have proved that that this is not a subspace. Let me actually get another one of these pages. Okay. All right, so now we're going to work on C here, and we're thinking about this set. So again, let me give you an example. What types of elements are in this set? Well, let's, if you look at, oh yeah, so let's see, x squared minus x plus 2. That's in this set. And how do I know that? This is an S. Because if I apply the transformation, just the rule that I was given, the rule that I was given says add up the coefficients on x squared and x. That's 1 plus -1. And then it says take 2 times this component here. So 2 times 2, and I get 0, 4. So this is one example of an object that's in S. Now, because we're going to disprove, we're going to show that this is not a subspace, we can show specific counterexamples, and that's enough. So here are some different options. Option one is to show that the 0 vector is not in here. So you could say, we know that the 0, I'll say it like this, that the 0 vector of P2R is z of x equals 0, which is the same as 0 times x squared plus 0 times x plus 0. Then, if I take the linear transformation of this polynomial, I'm going to get 0, 0, which is not 0, 4, and hence the 0 vector is not in S. So S is not a subspace. Not a subspace of P2. Okay, because the special thing about vectors in S is that when you apply the transformation, you get 0, 4. Well, that does not include the 0 vector. You can't put in the 0 polynomial and get 0, 4. So that's one option. Some people did that, which totally works. Option 2 is to show that this set is not closed under scalar multiplication. So let's just we're going to use a specific counterexample. So let's consider P of x equals, let's use the one that I mentioned earlier, x squared minus x plus 2. And let's get a scalar, I don't know, 3. Okay. Then if you're going to do a counterexample, you have to start with an element that's actually in your set. If you start with an element like some random polynomial that's not actually in this set, then you're not showing anything. You're not disproving anything because you're not even starting in the set. So you have to start with something that's in there. So then t of p of x here is t of x squared minus x plus 2. That does give us 0, 4, as I showed that earlier. So P is in S, but if we take T of K times P, in this case, T of 3 times x squared minus x plus 2, let's see what we get. We get T of 3x squared minus 3x plus 6. And let's apply the transformation to this now. It says add up these first two elements. So I get 3 minus 3. And then take 2 times whatever is over here. So 2 times 6. And I end up with 0, 12. In particular, that is not equal to 0, 4. So what happened here? I started with an element in S. That's very important. Then I multiplied by a scalar and I escaped. I got an element that I got something that's not in S. So 3 times x squared minus x plus 2 is not in S. So therefore, S is not closed under scalar multiplication. And hence is not a subspace of P2. Not a subspace of P2. So that was a second option. You could have, either one of these is fine and you would have gotten full credit. Now, sorry, I'll leave this on the screen for a second if you want to pause it and check, go through it on your own. There's a third option. The set is actually also not closed under addition. Now, there are some sets that fail like just one of these things, and those are still not subspaces. So if it fails any one of these, having the 0 vector, being closed under scalar multiplication or addition, then it's not a subspace. Okay, so it might satisfy one of these things, but not the other. So it has to have all 3 to be a subspace. So let's show that this is an option 3 you could have done, is show that S is not closed under under vector addition. Again, you have to start with elements that are actually in the set S. So let's consider that same, that same polynomial, this one. So this is in S. And let's consider Q of X. We have to pick another element of S. So let's say 2x squared minus 2x plus 2. That's also in S. Then I want to look at the transformation of P plus Q. And I want to see if I end up with something in S. And if I don't, then S is not closed under addition. So this is the transformation of x squared minus x plus 2 plus 2x squared minus 2x plus 2. That's the transformation of 3x squared minus 3x plus 4. And then I apply the transformation, which says add up these two terms, so 3 minus 3, and take 2 times this last term, so 2 times 4. And I end up with 0, 8, but that's not 0, 4. So P plus Q is not in S. And so S is not closed under addition. Therefore, S is not a subspace of P2 of R. Okay. So any one of these 3 options is fine, showing that it's not closed under addition, showing that it's not closed under scalar multiplication, or that it doesn't have the zero vector are all valid for this part of the problem. But just, I want to stress again, if you're going to do a counterexample, you have to start with something that's actually in the set. If I had just said like, oh, let's think about 2x squared minus 5x plus 7, that's not even an S, right? So 2x squared minus 5x plus 7, if I take the linear transformation of this, I'm going to get 2 plus -5 is -3, and 2 times 7 is 14. That's not 0, 4, so that's not even in there. Okay, so you have to start. If you're going to do a counterexample, you have to pick something in this set and then show that you escape that set by either multiplying by a scalar or adding two different elements of that set. Okay, cool. So I just wanted to go over that really quick. Let me know if you have any questions on this one, and good luck on the next skill check.